Welcome, listener, to the Deep Dive. Today, we're cutting right to the core of organic chemistry, the fundamental principles that don't just explain molecules, but really dictate how they operate.
Hmm.
From the subtle shifts in drug efficacy to, the very processes that sustain life itself, it all kind of boils down to these foundational concepts.
It really does.
This isn't just theory, it's like learning the underlying language of the molecular world.
That's absolutely the mission today.
Yeah.
Our deep dive is designed to, well, demystify these core ideas.
Good.
We're going to untangle everything from, say, the invisible forces of covalent bonding and how atoms meticulously arrange themselves in three-dimensional space
Yeah.
through hybridization,
Right, the 3D shapes.
exactly, to the dynamic dance of electrons that defines resonance, and the crucial roles of acids, bases, and functional groups in dictating how molecules interact.
So kind of the rules of engagement.
Precisely. Consider this a meticulously crafted shortcut, distilling your sources into essential insights that will help you truly grasp the bedrock of organic chemistry without feeling, overwhelmed.
Think of this deep dive as learning the alphabet and the grammar of molecular communication. Once you truly understand these essentials, the more complex, incredible stories of organic chemistry become not just understandable, but genuinely captivating. You'll start to see the hidden elegance and structures you might have once dismissed as just static formulas, and appreciate the intricate logic behind how everything fits together.
And we'll ensure you walk away with more than just definitions.
Yeah.
Our goal is for you to experience those aha moments where the pieces click into place.
Yeah, those are the best.
Where you connect what you're learning to real-world phenomena, making the complex accessible and memorable. So let's begin building our understanding from the ground up.
Okay, let's do it. Section 1, the Atomic Architects, Chapter 1, the building blocks. So let's dive right into what might seem like the most obvious question, but it's actually the most profound. Organic chemistry, this entire field, is dedicated almost exclusively to compounds involving carbon.
Yep, star of the show.
So what is it about carbon that makes it so incredibly special, so unique, that it earns its own massive branch of science? Is it just quantity, or is there something fundamentally different in its very nature?
That's a fantastic question, and it gets right to the heart of why we call it organic chemistry. The true insight here, the crux of carbon's starring role, is its unparalleled ability to form strong, stable, covalent bonds.
Strong and stable. Okay.
Yes. It can bond incredibly well not only with itself, forming long chains and intricate rings, but also with a vast array of other elements: hydrogen, oxygen, nitrogen, sulfur, the halogens, you name it.
So it's like the ultimate connector.
Kind of, yeah.
Yeah.
This isn't just about making a lot of molecules. It's about carbon's unique capacity to be a versatile scaffold for vastly different functionalities. We can think of it as the ultimate molecular Lego set, but with inherent instructions for building highly specific, intricate, and functional things.
So this fundamental versatility isn't just for building any molecule, but for building molecules with the very precise purposes and actions, right? This directed diversity must have huge implications.
Precisely. The true power lies in this directed diversity. Consider how this translates into the natural world and technology.
Okay.
Enzymes, for example, are giant carbon-based molecules in your body that can catalyze one specific reaction out of thousands with incredible efficiency.
Wow.
That precision is rooted in carbon's capacity to build a perfectly shaped active site, a sort of molecular hand-in-glove fit for its target.
Ah, I see.
In drug design, a subtle change in a carbon backbone, maybe just swapping a single atom or altering a bond's position, can transform a beneficial drug into an inactive compound or even a toxic one.
Right, tiny changes, huge effects.
It underscores that carbon's unique bonding isn't just about diversity, it's about crafting exact, stable, and highly functional molecular architectures.
And when you say endless variety, the sources you've shared really highlight some amazing examples, showcasing just how profound this versatility is, even within vastly different contexts.
Absolutely. The material underscores this vividly. Look at Figure 1.1, for instance, which illustrates this point beautifully. We have tetrodotoxin.
The pufferfish toxin?
Blue-ringed octopus venom here, but yeah, same family of toxins. A potent neurotoxin, a complex carbon-based molecule that causes rapid paralysis.
Scary stuff.
Definitely. Contrast that with vitamin C, a relatively simple carbon compound crucial for human health, found in rosehips, acting as a radical inhibitor.
Totally different function.
Totally different. Then there's carmine, a vibrant red pigment used as a dye, extracted from cochineal insects, again a carbon framework.
Huh. Didn't know that was carbon-based.
It is. And finally, morphine, the powerful pain-relieving alkaloid derived from opium poppies. Each of these molecules, with their profoundly different structures, origins, and biological activities, is a testament to carbon's incredible chemical adaptability.
It's really quite amazing.
They demonstrate how subtle changes in the arrangement of carbon atoms and other elements can lead to entirely distinct functions and properties.
That's truly amazing. So, this inherent ability of carbon to form such diverse, complex, and highly specific structures is our absolute starting point. It's the foundational principle that allows everything else in organic chemistry to exist and makes it the star of the show, as we've called it.
Exactly. That's the bedrock.
Okay, so moving on. Before we can even begin to think about building these elaborate carbon molecules, we need to zoom in even further to the invisible realm of electrons.
Right down to the subatomic level.
We need to understand where these electrons live, how they behave, and how their distribution dictates everything. We're talking about atomic orbitals, electron density, and these crucial yet invisible nodes regions within an orbital where the probability of finding an electron is actually zero.
Precisely. To truly grasp how electrons behave in these orbitals, it helps to think of them less as tiny planets orbiting a nucleus.
Which is how I learned it initially.
Yeah, the Bohr model picture. It's better to think of them more as diffused clouds of probability, or even a standing wave of energy within specific regions around the nucleus.
Like a wave. How does that work?
Think of those nodes like the still points on a vibrating guitar string. The electron wave simply doesn't exist there.
Ah, okay.
This isn't just a quirky detail. These nodes define the distinct three-dimensional shapes of orbitals and critically dictate how atoms approach and bond with each other.
So it's not a uniform cloud, but rather specific probability fields where electrons are most likely to be found, and some where they definitely are not.
Uh,
How do these different orbitals look in this probability landscape?
That's right. Consider the simplest, the 1s orbital. It's a spherical cloud with its highest electron density right at the nucleus, decreasing exponentially as you move outwards.
Simple sphere. Got it.
It's a beautifully simple symmetrical form. But then, if we move to the 2p orbital, it's a very different story.
Okay.
The 2p orbital has that familiar dumbbell shape because it features a distinct nodal plane passing directly through the nucleus.
So like a flat plane cutting through the middle.
Exactly. This means there's absolutely zero chance of finding the electron at the nucleus itself or anywhere on that central plane. Understanding these distinct shapes and electron distributions is fundamental because these are the very spaces where atoms will overlap their electron clouds to form covalent bonds.
Okay, so once we've peered into that invisible electron world and understood these orbital shapes, how do we take that fundamental insight and translate it into a practical visual blueprint for how atoms actually connect to form molecules?
Right, how do we draw this?
This is where Lewis structures become our essential shorthand, the first word in our molecular language.
Exactly. Lewis structures provide that foundational visual grammar for us. There are indispensable shorthand for depicting valence electrons, those outermost electrons involved in bonding, and their arrangement in molecules.
Makes it easier to apply the octet rule, right?
Absolutely. While many of you listening are familiar with it, it's worth a quick recap. Atoms tend to gain, lose, or share electrons to achieve 8 valence electrons, mimicking the stable configuration of noble gases.
The magic number 8.
Pretty much. Lewis structures are especially crucial for predicting bonding patterns for the most common elements in organic chemistry: carbon, hydrogen, oxygen, nitrogen, and the halogens.
The usual suspects.
Usual suspects, yes. We visually distinguish between single bonds, where one pair of electrons is shared, double bonds, with 2 shared pairs, and triple bonds, involving 3 shared pairs between 2 atoms.
1 line, 2 lines, 3 lines.
Basically, these representations aren't just arbitrary. They tell us precisely how many electron pairs are involved in holding atoms together, which, as we'll see, dictates so much about the molecule's shape and reactivity.
So it's about seeing at a glance how many electrons are involved in each connection, right? And the sources highlight a critical problem-solving hint related to this that we can't afford to overlook.
Yes, and this problem-solving hint is actually a foundational rule, a non-negotiable principle, especially for second-row elements like boron, carbon, nitrogen, oxygen, and fluorine.
Okay, what's the rule?
These elements can never have more than 8 electrons in their valence shells. Never ever.
Right. No exceptions for those ones.
None. This is because they only have access to 2s and 2p orbitals. They don't have low-energy d orbitals available to expand their octet-like elements further down the periodic table can.
Ah, okay, that makes sense. Physically impossible for them.
Exactly. This rule is crucial for identifying invalid Lewis structures and ensuring we're predicting correct bonding. For example, if you draw 10 electrons around a nitrogen atom, you immediately know that structure is incorrect.
So that's a big no-no, right?
Mhm.
A fundamental check.
It's a fundamental checkpoint in understanding covalent bonding and how these elements behave in molecules. Absolutely critical.
Okay. So Lewis structures give us the electron count and connectivity on a two-dimensional page, but molecules don't exist in two dimensions, do they?
Definitely not. They live in 3D.
They occupy dynamic three-dimensional space, and that precise shape dictates everything about their function. So how do we go from a flat drawing to understanding a molecule's true architectural form? This is where the truly elegant concept of hybridization comes alive.
That's a fantastic question, and it's precisely where hybridization offers a profound answer. Molecules aren't flat because electrons, well, they repel each other. They want to get as far apart as possible.
Naturally, like charges repel.
Right. Hybridization describes a theoretical process where atomic orbitals, those S and P orbitals we just discussed, effectively blend together, they sort of average out, to form new equivalent hybrid orbitals.
New orbitals from old ones.
Exactly. These hybrid orbitals are then oriented in space in a way that minimizes electron repulsion and allows for optimum bond angles in molecular geometry. This optimization is all about achieving the lowest energy state, leading to very specific, stable, three-dimensional shapes.
Lowest energy equals most stable shape.
You got it. And a key rule to remember is that the number of hybrid orbitals formed always precisely equals the number of atomic orbitals combined. We don't lose or gain orbitals in the process.
Conservation orbitals, makes sense. So what are the primary types of these hybrid orbitals that we'll encounter in organic molecules, and how do they lead to different shapes?
We predominantly encounter three critical types in organic chemistry. First, sexp3 hybridization.
Okay, sp3.
This involves one s orbital and all three p orbitals combining to form four equivalent sp3 hybrid orbitals.
1s, 3p's, makes 4 sp3s.
Perfect. These four hybrid orbitals are directed towards the corners of a tetrahedron, giving us the familiar bond angles of approximately 109.5 degrees.
Like methane, right? The classic tetrahedral molecule.
Methane is the textbook example, yeah, where carbon is bonded to four hydrogen atoms. It's that iconic tetrahedral shape.
Got it.
A subtle but important nuance is that lone pairs of electrons, for instance on the nitrogen and ammonia, occupy a bit more space than bonding pairs.
Oh, interesting. Why is that?
Well, they're only held by one nucleus, not two, so they spread out a bit more. This can slightly compress the bond angles from the ideal 109.5 degrees, so ammonia's angles are a little smaller.
Okay, subtle effect, but important. What's next?
Second, sp2 hybridization. Here, one s orbital combines with two p orbitals to form three sp2 hybrid orbitals.
1s, 2p's. 3 sp2s, leaving 1 p orbital behind.
Exactly, you're ahead of me. These three sp2 orbitals are arranged in a trigonal planar geometry, meaning they lie in a flat plane with bond angles of about 120 degrees.
Flat, like a triangle.
Yep. And crucially, that single unhybridized p orbital remains, lying perpendicular to the plane of the sp2 orbitals, like sticking straight up and down from the flat triangle.
And that leftover p orbital is important.
Absolutely essential for the formation of double bonds, as we'll soon see.
Okay, holding on to that thought. What's the third type?
And third, sp hybridization. This involves one s orbital and only one p orbital, forming two sp hybrid orbitals.
1s, 1p, 2 sps, now leaving 2 p orbitals unused.
Precisely. These two sp orbitals arrange themselves linearly, resulting in bond angles of 180 degrees. Straight line.
Linear, okay.
And in this case, those two remaining unhybridized p orbitals are vital for the formation of triple bonds. Understanding these geometries, tetrahedral, trigonal planar, linear, is the first step to truly visualizing a molecule structure.
That makes perfect sense for the geometry. And this leads us directly to a critical distinction. Sigma versus pi bonds, which explains why some parts of a molecule are rigid while others can freely rotate, correct?
Absolutely. This is a fundamental principle. The first bond formed between any two atoms is always a sigma.
Oxygen bond.
Yes. This results from the head-on, direct overlap of either hybrid orbitals or a hybrid orbital and a supervised orbital. Think of it as a direct, strong connection.
Okay.
These sigma bonds are strong and cylindrically symmetrical, meaning rotation around them is typically free and requires very little energy. like spinning a pencil along its axis.
Easy rotation. Got it.
However, any subsequent bonds between those same two atoms, the second bond in a double bond, or the second and third bonds in a triple bond, are pi bonds.
Pi bonds. Okay, the extra one.
Exactly. These are formed by the side-by-side overlap of the remaining unhybridized p orbitals. Those ones we said were left over, that's where they come in.
Ah, the one sticking up and down, side-to-side overlap.
That's the picture. It's a weaker overlap than sigma, and it's definitely not cylindrically symmetrical.
So this explains the rigidity you mentioned for double bonds. Can you give us an illustrative example that really highlights this difference?
Certainly. Let's compare ethylene, which has a carbon-carbon double bond, with ethane, which has a carbon-carbon single bond.
Okay, ethane versus ethylene.
In ethane, C2H6, the carbon atoms are CP3 hybridized, and the CC bond is a pure sigma bond. Because of its cylindrical symmetry, the methyl groups, CH3, can freely rotate around that CC single bond. It spins easily.
Like beads on a string.
Good analogy. This leads to various transient shapes or conformations. Now look at ethylene, C2H4, where the carbons are CP2 hybridized. The double bond consists of one sigma bond and one pi bond.
Sigma plus pi.
Right. That pi bond, formed by the side-by-side overlap of the unhybridized p orbitals above and below the sigma bond, effectively locks the molecule into a planar arrangement.
Locks it flat.
Exactly.
Right.
If you were to try and twist the molecule around that double bond, you would literally have to break the side-by-side overlap of those p orbitals. You'd destroy the pi bond.
And that takes energy.
A significant amount of energy, yes. This makes double bonds and triple bonds rigid and prevents free rotation. This inherent rigidity, directly explained by the presence and nature of pi bonds, profoundly influences a molecule's overall shape, its stability, and ultimately its chemical reactivity.
So it's not just a static feature, it dictates how it behaves.
Absolutely. In biological systems, think of how proteins have very precise 3D structures. If a double bond somewhere in that protein's backbone was subtly flexible, it could completely change its shape, rendering it useless.
Wow. Yeah, shape is function.
Or in material science, designing polymers with specific rigidity for, say, a sturdy plastic versus a flexible film often comes down to the number and placement of these pi bonds.
That's a powerful connection. So understanding hybridization and the formation of these sigma and pi bonds isn't just about drawing pretty shapes. It's truly essential for predicting a molecule's precise three-dimensional structure, how it will orient itself, and consequently how it will interact with other molecules in its environment.
Exactly. It's the architecture that defines its function.
Okay, moving on. We've established that Lewis structures give us a valuable two-dimensional snapshot of electron distribution. But sometimes, a single Lewis structure just isn't enough to accurately describe the true dynamic electron distribution within a molecule.
Right. Sometimes one picture doesn't tell the whole story.
It's like trying to capture a moving target with the still photograph. You get one moment, but not the full fluid picture. That's where resonance structures come in, allowing us to describe a molecule as a hybrid, or a blend of multiple contributing forms.
That's a perfect analogy. Resonance is really about electron delocalization, the spreading out of electron density or charge over two or more atoms.
Delocalization, spreading out.
Yes, and this delocalization isn't just an academic concept. It provides significant, often profound, stability to the molecule.
So it makes the molecule more stable. How?
The key insight here isn't just that electrons move, but that this electron delocalization distributes energy, making the molecule inherently more stable. Imagine spreading a heavy load across multiple supports instead of just one. It's much more robust.
Okay, spreading the load makes it stronger, more stable. Got it.
When drawing resonance forms, it's crucial to remember a cardinal rule. Only electrons can be delocalized. The nuclei of the atoms must remain in their exact, fixed positions.
No moving atoms.
No moving atoms. Maintain identical bond distances and angles across all resonance contributors. We're not moving atoms, we're just depicting different ways to distribute the electrons within the same atomic framework.
And how do we visually represent this movement of electrons from one resonance form to another? There's a specific universal notation that becomes incredibly important here, right? The curved arrows.
Yes, this is where curved arrows or electron-pushing arrows become our indispensable visual language. These arrows are the fundamental tools for illustrating the precise movement of electron pairs.
Okay, so how do they work?
The arrow always starts from an electron-rich site, typically a lone pair of electrons or a pi bond, and points directly towards an electron-deficient site, indicating where that electron pair is forming a new bond or becoming a new lone pair.
From electron source to electron sink.
Essentially, yes. Mastering electron pushing and resonance structures is one of the most fundamental skills in organic chemistry. It allows us to predict reaction mechanisms and understand reactivity. It's the language of electron flow.
So once we've identified multiple possible resonance forms for a molecule, are they all equally important? Or do some contribute more significantly to the molecule's overall character?
That's a fantastic and crucial question because, no, not all resonance forms are equal. We have a set of general rules to evaluate their relative importance as contributors to the overall resonance hybrid.
Okay, how do we rank them?
The more stable a resonance form is, the more it contributes to the molecule's true electron distribution. First, we aim for the maximum number of octets and the maximum number of bonds. Structures that successfully fulfill the octet rule for all second-row elements and possess more covalent bonds are generally more stable.
More bonds, more octets, better.
Generally, yes. More significant contributors to the hybrid. Second, we strive to minimize charge separation.
Keep charges close, or better yet, neutral.
Exactly. Forms that have positive and negative charges separated, especially widely separated, are typically minor contributors and are higher in energy. They contribute less to the overall character of the molecule because creating charge separation costs energy.
Okay, major versus minor contributors. Can you give us a concrete example to illustrate how these rules apply and what they tell us about a molecule?
Certainly, formaldehyde, with its carbon-oxygen double bond, H2CO, is a classic example. Its primary, or major contributor, depicts a neutral molecule with the double bond satisfying octets.
The standard picture.
Right. However, we can also draw a minor contributing resonance form. In this form, we can push one of the electron pairs in the pi bond up onto the more electronegative oxygen.
Okay, moving the pi electrons.
Yes, this creates a negative charge on oxygen and leaves the carbon with only 6 electrons and a positive charge.
So C plus and O, that's charge separation.
Exactly. This polar resonance form is considered a minor contributor because it has charge separation and fewer bonds, the CO bond became a CO single bond, than the neutral structure.
Makes sense. Less
Yeah.
stable.
Less stable, so it contributes less. But even though it's minor, it's not insignificant. It explains why the carbon-oxygen double bond in formaldehyde has a significant dipole moment, with the oxygen carrying a partial negative charge and the carbon a partial positive charge.
Ah, so the minor form still tells us something important about polarity.
Precisely. This inherent polar character, informed by the minor resonance form, is crucial for understanding formaldehyde's reactivity, especially how it attracts electron-rich species, nucleophiles, to that partially positive carbon.
I see.
This type of electron delocalization is why, for example, a carboxylic acid is vastly more acidic than an alcohol, or why a molecule like benzene, which we'll encounter later, is incredibly stable because its electrons are perfectly delocalized in a ring. It changes the entire reactivity profile.
Often in ways that dictate fundamental biological processes, right?
Absolutely. It changes the entire reactivity profile, often dictating biological function or chemical behavior.
That really brings it to life. So resonance is a powerful concept because it moves us beyond a single static picture and helps us understand a molecule's true dynamic electron distribution, which in turn dictates its resulting stability and how it will react with other chemical species.
Exactly. It's truly foundational for predicting reactivity.
Okay, let's move into section 2. The rules of engagement, chapter 2. Reactivity and interactions.
Right, how molecules interact.
Now that we've got our molecules built with their specific shapes and dynamic electron distributions, how do they talk to each other? What makes some molecules stick together tightly, requiring a lot of energy to separate, while others just slip past each other easily?
Yeah, the social life of molecules.
It all comes down to molecular polarity and the invisible but incredibly powerful intermolecular forces.
Precisely. Molecular polarity is a critical property, and it originates from individual bond-dipole moments.
Okay, remind us what those are.
These arise from the unequal sharing of electrons between atoms in a covalent bond, which happens due to differences in electronegativity.
The pull on electrons.
Right. When atoms with different electronegativities bond, the more electronegative atom pulls the shared electrons closer to itself, creating a partial negative charge on that atom and a partial positive charge plus on the less electronegative atom.
Like a tiny magnet within the bond?
Sort of, yes.
Yeah.
The molecular dipole moment is then the vector sum of all these individual bond-dipole moments within the entire molecule. Its magnitude and direction are absolutely crucial for understanding how the molecule will behave.
And your sources really highlight that lone pairs of electrons also play a surprisingly significant role in this overall polarity. They're not just sitting there.
Critically so. Lone pairs of electrons, those not involved in bonding, also contribute significantly to a molecule's overall dipole moment. They represent a localized region of concentrated negative charge.
Ah, a blob of negativity.
Effectively, yes. Pushing the electron density to one side of an atom and thus heavily influencing the molecule's overall polarity. If you were to look at electrostatic potential maps, the red areas, indicating regions of high negative potential, vividly show where these lone pairs are located.
Like in water or ammonia.
Exactly. In water or ammonia, those lone pairs contribute substantially to the molecule's strong dipole moment, making them highly polar molecules.
So it's not just about the bonds then, but also the non-bonding electrons acting as localized charges. Can you give us a contrasting example of how a molecule's overall three-dimensional geometry can dramatically affect its polarity even if it has polar bonds?
Of course. Let's compare carbon tetrachloride, CCl4, with chloromethane, CH3Cl.
Okay, CCl4 versus CH3Cl.
Both molecules contain polar carbon-chlorine bonds because chlorine is significantly more electronegative than carbon, so each CCl bond has a dipole moment, a definite pole.
Makes sense. Both have polar bonds.
However, CCl4 has a molecular dipole moment of 0. It's nonpolar overall.
Wait, how? With four polar bonds?
Because its highly symmetrical tetrahedral geometry means that the four individual CCl bond dipoles are perfectly oriented to cancel each other out in 3 dimensions. The poles all balance perfectly.
Ah, the symmetry cancels it out.
Exactly.
Yeah.
All those individual poles on electrons sum to a net 0. Chloromethane, CH3Cl, on the other hand, lacks this perfect symmetry. It only has one strong CCl bond dipole and 3 much less polar CH bonds.
So they don't cancel.
Right. Its individual bond dipoles do not cancel out. This results in a significant net molecular dipole moment, making chloromethane a polar molecule.
Right.
So the shape truly dictates the overall polarity.
That's a really clear picture. So this overall molecular polarity isn't just an abstract concept. It directly dictates practical things like how molecules interact, like their solubility properties, doesn't it? The famous, dissolves like.
Absolutely. The guiding principle for solubility is famously stated as like dissolves like. This means polar substances generally dissolve well in polar solvents, and nonpolar substances dissolve well in nonpolar solvents.
Okay, but why does dissolve like?
The reason is rooted in intermolecular forces. For a substance to dissolve, the attractions between solute molecules must be overcome, and the attractions between solvent molecules must also be overcome. That takes energy.
Breaking old attractions.
Yes, this requires strong enough new intermolecular forces, such as hydrogen bonds, dipole attractions, and London dispersion forces, to form between the solute and solvent. These new attractions must be strong enough to compensate for the energy expended in breaking the original attractions.
Yeah, the new attractions have to be worth it, energy-wise.
Pretty much. Can I walk you through the different scenarios?
Please do. Give us the examples.
Okay, let's start with the classic example. Dissolving sodium chloride, salt, a highly polar ionic solute, in water, a highly polar solvent.
Polar and polar. Should work.
It does. Water molecules, with their strong polarity, can effectively surround and hydrate the individual sodium and chloride ions. The partial negative oxygen attracts Na, plus A, the partial positive hydrogens attract Cl. This strong solvation releases a large amount of energy, which is nearly sufficient to overcome the strong electrostatic attractions, lattice energy, holding the ions together in the crystal. This, plus an increase in randomness, allows the salt to dissolve readily. That's polar solute and polar solvent, but they like each other.
Makes sense. What about nonpolar?
Now, consider a nonpolar solute in a nonpolar solvent, like oil in gasoline. Both are nonpolar, so they primarily interact via weak London dispersion forces, just temporary fleeting dipoles.
Weak forces all around.
Right. These weak forces are easily overcome, and new, similarly weak forces form between the oil and gasoline molecules, so they readily mix. Nonpolar dissolves nonpolar. Easy.
Okay, now the opposites.
Then there's the dislikes-like scenario.
Okay.
A polar solvent in a nonpolar solvent, like salt in gasoline. This simply won't work.
Why not?
The nonpolar molecules of gasoline cannot form strong enough attractions with the charged sodium and chloride ions to overcome their immense lattice energy. The gasoline molecules just can't pay the energy cost to break the salt crystal apart, so the salt remains undissolved.
Not enough attraction. Got it. Last case.
And finally, a nonpolar solute in a polar solvent, like oil and water. Famously, they don't mix.
Oil and water, yeah.
The polar water molecules prefer to interact strongly with each other, forming extensive networks of hydrogen bonds. They're quite happy together.
Okay.
Allowing the nonpolar oil molecules in the sol would require breaking those strong water attractions to make space. but the oil can't offer strong attractions back to the water in return. The energy cost is too high, so they stay separate.
Water molecules stick together and exclude the oil.
Essentially, yes. Each case tells a clear story of molecular preference driven by these invisible intermolecular forces.
That's a really comprehensive picture. So understanding these molecular polarities and the resulting intermolecular forces is absolutely fundamental. It helps us predict not just boiling points and melting points, but crucially, how compounds will behave in solution.
Which is critical for everything from biological processes within our bodies to large-scale industrial chemistry.
Yeah.
It dictates how things mix, react, and function.
Absolutely. Okay, next big topic, acids and bases. If molecular polarity is all about attraction and how molecules socially interact, then acids and bases are about donation and acceptance.
Giving and taking.
Often of protons, but sometimes, as we'll see, of electron pairs. These fundamental concepts are truly the cornerstones of virtually all organic reactions, dictating how molecules transform, build, and break down.
Indeed. We primarily view acid-base chemistry through two incredibly powerful lenses, both of which are deeply intertwined with the critical concept of electron pushing we mentioned earlier.
Okay, what's the first lens?
First, the Bronsted-Lowry acids and bases definition. This perspective focuses explicitly on the transfer of a positively charged proton, an H+ found.
Just the proton, H+ then.
Right. A Bronsted-Lowry acid is defined as any species that donates a proton, while a Bronsted-Lowry base is any species that accepts a proton. It's all about proton transfer.
Acid donates, base accepts. Simple enough.
It broadens our understanding beyond just aqueous solutions. For example, a hydroxide ion, OH, which is an Arrhenius base, functions as a Bronsted-Lowry base by actually accepting a proton to form water, H2O.
Okay, so it includes things Arrhenius didn't cover as clearly.
Exactly. This framework is essential for understanding proton transfer reactions, which are ubiquitous in organic chemistry.
So how do we quantify the strength of these acids? What makes one acid stronger or weaker than another, and how do we measure that? Is there a scale?
That brings us to quantifying acid strength through Ka and pK values. The strength of an acid is quantitatively measured by its acid dissociation constant, Ka. It tells you how much it dissociates in water.
Ka. Okay.
However, more commonly and conveniently, we use its pK value, which is simply the negative logarithm of Ka, pKa nes log Ka.
pKy the P, like pH.
Exactly like pH. It turns awkward scientific notation numbers into more manageable ones. Remember, because of the negative log, a lower pK value indicates a stronger acid.
Lower pKa, stronger acid. Got it.
For context, strong inorganic acids, like hydrochloric acid, HCl, typically have pAcyl values around 0 or even negative, meaning they fully dissociate in water. Boom, all protons gone. Okay.
And organic acids.
Most organic acids, however, are considered weak acids and possess pK values generally greater than 4. So if you see a pKa 5, it's a weak acid. If it's 2, it's stronger. If it's a -2, it's very strong. The inverse relationship between pK and acid strength is key.
And this quantitative knowledge is incredibly useful because it allows us to predict the direction of an acid-base reaction, doesn't it? Which way will it go?
Absolutely. This knowledge is incredibly powerful for predicting the equilibrium position of acid-base reactions. In any Bronsted-Lowry acid-base reaction, the equilibrium will favor the products if the reacting acid is stronger, lower pKa, than the conjugate acid formed on the product side.
Okay, reaction goes from stronger acid to weaker acid.
Exactly. Or, to put it more simply, the reaction tends to proceed in the direction that forms the weaker acid and the weaker base. Nature favors stability, the less reactive species.
Weaker acid, weaker base wins. Makes intuitive sense.
For example, if you react to strong acid, like HCl pKa-7, with a relatively strong base, like hydroxide, forming water, pKa 15.7, the equilibrium will lie extremely far to the right, favoring the formation of the much weaker conjugate acid, water, and weaker conjugate base, ClO. This predictive power is a core skill.
That's a clear rule to remember. But what structural factors actually determine the strength? What makes one molecule a stronger acid than another? Why does HCl have a pKa of -7 and acetic acid a pKa of 4.7?
The key to answering that question is to consider the stability of its conjugate base. When an acid donates its proton, it forms a conjugate base, which carries a negative charge, or is less positive.
Right, the thing left behind after proton leaves.
Yes. Any factor that stabilizes this negative charge on the conjugate base will, by definition, make the original acid stronger, because the conjugate base is happier, more stable being formed.
Stable conjugate base, stronger acid. Okay, what stabilizes it?
There are two primary structural factors your sources highlight. First, electron withdrawing groups, EWGs.
Okay, what do they do?
These groups, Due to their inherent electronegativity, like halogens, oxygen, nitrogen, can pull electron density away from the atom bearing the negative charge in the conjugate base. This effectively spreads out or delocalizes that negative charge through the sigma bonds, making it less concentrated and therefore more stable.
Pulling electrons away stabilizes the negative charge. Example.
For instance, consider chloroacetic acids. Acetic acid, CH3COOH, has a pK of about 4.7. Monochloroacetic acid, ClCH2aCOH, with one electron withdrawing chlorine atom near the acidic proton, has a pK of around 2.8, much stronger.
Wow, big difference from one chlorine.
It gets better. Dichloroacetic acid, Cl2CHCOH, is even stronger, with a pK of 1.2. And trichloroacetic acid, Cl3COAH, is a very strong acid with a pK of 0.7.
Whoa.
The increasing number and proximity of the electron-withdrawing chlorine atoms stabilize the negative charge on the carboxylate conjugate base more and more, making the acid progressively stronger.
Okay, EWGs are one factor. What's the second?
Second, and often even more profoundly, resonance stabilization.
Ugh, resonance again. Spreading the charge through pi bonds this time.
Exactly. Spreading a negative charge over multiple atoms through electron delocalization, which we just discussed with resonance structures, is an extraordinarily effective way to stabilize a conjugate base, significantly enhancing the acid's strength.
More effective than just pulling through single bonds?
Generally, yes, because it shares the charge over multiple atoms more directly.
Hmm.
This effect is very evident in acids that have carbonyl CO groups adjacent to the atom donating the proton, like in carboxylic acids, RCOH.
Okay.
The negative charge of the carboxylate anion, RCOO, the conjugate base, is delocalized equally over two oxygen atoms via resonance. You can draw two equivalent resonance structures.
Sharing the load between two oxygens.
Right. This makes carboxylic acids vastly stronger acids, pKa 4 to 5, than, say, simple alcohols, ROH, pKa 1618, where the negative charge on the alkoxide conjugate base, RO, is localized entirely on a single oxygen atom. No resonance stabilization there.
Huge difference in pK. Resonance is powerful.
It is. This is a prime example of how electron pushing and resonance structures profoundly influence molecular reactivity and properties like acidity. Understanding how to stabilize that negative charge gives us incredible predictive and design power.
Like for designing drugs or catalysts.
Exactly. If you're a medicinal chemist trying to make a drug more soluble or interact better with a target, you might introduce an electron withdrawing group or engineer resonance stabilization to tune the acidity or basicity of certain parts of the molecule. It's chemical engineering at the molecular level.
Fascinating. So if Bronsted-Lowry theory is all about the donation and acceptance of protons, is there an even more fundamental way to think about acid-base interactions that goes beyond just protons? You mentioned electron pairs earlier.
Absolutely. The Lewis acid-base theory expands our view considerably. It focuses purely on electron pairs.
Okay. How does Lewis define them?
A Lewis acid is defined as an electron pair acceptor, anything that can accept a pair of electrons. We also call these electrophiles, meaning electron-loving species.
Electrophile equals Lewis acid equals electron acceptor. Got it. And the base.
Conversely, a Lewis base is an electron pair donor, anything with a pair of electrons to give, also known as a nucleophile, meaning nucleus-loving species, since it's attracted to positive or electron-deficient centers.
Nucleophile equals Lewis base equals electron donor.
Okay. This is a much broader definition because it encompasses all Bronsted-Lowry reactions, where the proton, H plus air, acts as the electron pair acceptor, the electrophile.
Ah, so Bronsted-Lowry is just a specific type of Lewis reaction.
Essentially, yes. But the Lewis definition also includes many reactions where there's no proton transfer at all. It shifts our focus completely to the fundamental movement of electron pairs.
And this is where our curved arrows become even more central, isn't it? They're not just for resonance, they're the language for all electron movement in reactions.
Exactly. This is where electron pushing becomes the universal language of organic chemistry reactions. Curved arrows are not just conceptual tools. They are the visual representation of the actual flow of electrons in these reactions, showing bonds breaking and forming.
Remind us of the arrow rule again.
The arrow always starts from an electron-rich site, which is our Lewis base or nucleophile, such as a lone pair or a pi bond, and points directly towards an electron-deficient site, which is our Lewis acid or electrophile, like an atom with a positive charge or an empty orbital.
From rich to poor, always.
Always. Mastering electron pushing is critical for understanding and predicting almost every organic reaction mechanism. It shows you how the transformation happens, step by step.
Can you give us a quick example of a Lewis acid-base reaction that wouldn't typically be classified as a Bronsted-Lowry reaction, something without protons?
Sure. Imagine a lone pair on a nucleophile, like the nitrogen and trimethylamine, CH3,3N,
Okay, nitrogen with a lone pair.
directly attacking the empty orbital of a Lewis acid like boron trifluoride, BF3. Boron in BF3 only has 6 valence electrons. It hasn't got an octet, making it very electron deficient.
Hungry for electrons.
Exactly. The curved arrow starts from the lone pair on the nitrogen and points directly to the boron atom, forming a new coordinate covalent bond between N and B.
So the nitrogen donates both electrons for the new bond.
Precisely. There's no proton transfer involved anywhere, but it's a clear donation and acceptance of an electron pair, perfectly fitting the Lewis definition. This simple example highlights the expansive reach of Lewis acid-base theory.
Understanding both Bronsted-Lowry and Lewis acid-base concepts and mastering the art of electron pushing with those curved arrows truly provides the fundamental framework for comprehending almost all organic reaction mechanisms.
It's how we dissect and predict chemical transformations. It's the core logic.
Okay, final part of this section, functional groups. We've been discussing the foundational rules of bonding and reactivity, and now we need to talk about the specific parts of a molecule that dictate its characteristic reactions.
Right, the action centers.
These are our functional groups, and they truly give each molecule its unique chemical personality and reactivity profile.
Indeed. Functional groups are specific arrangements of atoms within a larger molecule that are the primary sites of chemical reactivity. They are the hotspots, the active centers.
The interesting bits.
Often, yes. They largely determine a molecule's personality, how it will behave, what types of reactions it will undergo, and how it will interact in different chemical environments. The rest of the molecule, often represented by the R symbol, can be quite large and boring, chemically speaking.
Yes, the R symbol. Speaking of that, what exactly does it stand for? We see it all over the place in organic chemistry.
The R symbol is incredibly useful shorthand. It lets us focus on the functional group by representing the rest of the molecule, usually an alkyl group, which is essentially any chain or branch made up of just carbon and hydrogen single bonds.
So the non-reactive framework.
Generally, yes. It's the chemically quieter, more stable part, letting us spotlight the dynamic, active center of the molecule, the functional group itself. This simplifies drawing and discussing reactions without getting bogged down in the minutiae of long carbon chains that aren't changing.
Okay, makes sense. So let's explore a few of these essential functional groups. What makes them unique, and how do they give a molecule its distinct personality?
Let's delve into a couple of key ones that highlight this idea of molecular personality. First, alcohols, which have the general formula ROH.
The OH group.
Yes, they contain a hydroxy group, OH, bonded to a saturated carbon atom. The oxygen atom is highly electronegative, making the OH bond very polar, and crucially, allowing alcohols to form strong hydrogen bonds with themselves and with other polar molecules like water.
Hydrogen bonding, that affects boiling points and solubility, right?
Absolutely. It significantly influences their physical properties, giving them higher boiling points than similarly sized hydrocarbons and making smaller alcohols soluble in water. But beyond physical properties, that OH group brings multiple facets of reactivity.
Oh, like what?
Well, the hydrogen atom on the oxygen can be acidic, though weakly, as we saw at pico-A16. The oxygen atom's lone pairs make it a nucleophile, an electron donor, a Lewis base. And the carbon atom attached to the oxygen can also be a site of reaction, an electrophilic site in some reactions.
Wow, okay. So in one small functional group, you have multiple potential reaction sites.
Exactly. Multiple personalities, if you will. They consider amines, represented as RNH2, primary, R2NH, secondary, or R3N, tertiary.
Nitrogen-based groups.
Right. These are alkylated derivatives of ammonia, meaning one or more hydrogens on ammonia, NH3, have been replaced by alkyl R groups. Like ammonia, amines are typically basic.
I like basic.
Due to the lone pair of electrons on the nitrogen atom. This lone pair is readily available to accept a proton, making them Bronsted-Lowry bases, or to donate that electron pair, making them Lewis bases, nucleophiles.
So they can grab protons or attack electron pore centers?
Precisely. Their basicity and nucleophilicity are fundamental to countless biological processes. Think amino acids, DNA bases, and synthetic reactions. Many neurotransmitters like dopamine and serotonin are amines, and their basicity is crucial for their function.
Very important biologically. What about groups with CO?
Ah, the carbonyl group 11. This is the heart of many functional groups like aldehydes, RCHO, and ketones, RCOR, carboxylic acids, RCOH, esters, RCOA, amides, RCONH2. It's everywhere.
The C double bond O, what's special about it?
The carbon-oxygen double bond is highly polarized because oxygen is much more electronegative than carbon, pulling electron density towards itself. Remember our formaldehyde resonance structure.
Yeah, partial positive on carbon, partial negative on oxygen.
Exactly. This makes the carbonyl carbon electron deficient, partially positive, and therefore an electrophilic site highly susceptible to attack by nucleophiles, electron donors. The pi bond can also break easily in addition reactions.
So it attracts nucleophiles to the carbon.
Very much so. The distinction between an aldehyde, where the carbonyl carbon has at least one H attached, and a ketone, where it has two R groups attached, leads to significant differences in reactivity, with aldehydes generally being more reactive.
Even though they both have the CO.
Yep, subtle structural differences matter. And there are others like ethers, art-Ri, nitriles, RCN, amides, RCO, and H2, each with its own unique reactivity pattern based on the atoms involved and their arrangement.
That's a powerful way to look at it. These functional groups are essentially the active sites, the specific regions within a molecule that truly guide us in predicting how that molecule will react and what chemical transformations it can undergo.
They are the keys to unlocking a molecule's entire chemical story and understanding its behavior. Learn the functional groups, learn their typical reactions, and you're well on your way.
Fantastic. Okay, let's move into our final section, Section 3, Structural Diversity, Chapter 3, Alkenes, 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 and Isomers.
Building the skeletons and seeing how they differ.
So with our now deep understanding of bonding, molecular shapes, and the specific functional groups that define reactivity, we can zoom out a bit and look at how these elements come together in the brightest sense. Classifying hydrocarbons.
Right, back to basics.
These are the simplest organic compounds, the basic skeletons upon which all more complex structures are built.
That's right. Hydrocarbons, as their name explicitly suggests, are compounds made exclusively of carbon and hydrogen atoms, C and H only. Their classification is absolutely fundamental in organic chemistry and depends critically on the types of bonds present between the carbon atoms, single, double, or triple. That's the first question.
And those bond types dictate everything.
They fundamentally dictate the properties and reactivity of the entire molecule, setting the stage for everything else.
What are these core classifications then, and what makes each one distinct?
We have several main categories, each with its own defining characteristics. First, alkenes.
Alkenes, heard of those? Methane, ethane, propane.
Exactly. These are hydrocarbons that contain only single bonds between their carbon atoms. CC single bonds only.
Saturated, right. Maxed out on hydrogens.
Precisely. Because they have the maximum possible number of hydrogen atoms for their carbon skeleton, they are called saturated hydrocarbons. Alkenes are interesting because they are characterized by being relatively unreactive.
Paraffins. Too little affinity.
That's the old name, yes. From the Latin parum affinis, meaning too little affinity. Imagine naming a compound the antisocial one because it just doesn't want to react with other chemicals.
Huh. But that stability is useful, right? Fuels.
Absolutely. This very lack of reactivity makes them incredibly useful as stable fuels, gasoline, natural gas, and lubricants.
Okay, so alkanes are the stable, single-bonded ones. What's next?
Next, we have alkanes. These are characterized by the presence of one or more carbon-carbon double bonds.
That's a functional group itself.
It absolutely is. Those pi electrons we discussed earlier create a region of increased electron density, making alkenes much more reactive than alkenes, particularly towards electrophiles. Those electron-loving species are attracted to the pi cloud.
So the double bond is a site of reactivity.
Definitely. And remember, this double bond also introduces rigidity, no free rotation.
Right. The cis-trans thing comes in here. Okay, after alkenes.
And there are alkenes, which are defined by the presence of one or more carbon-carbon triple bonds.
Triple bonds. Even more reactive.
Generally, yes. Like double bonds, these triple bonds are also highly reactive functional groups due to their even more concentrated electron density, 2 pi bonds, and the linear hybridization. They undergo similar, though often more vigorous, reactions than alkenes.
Okay. Alkenes, alkenes, alkanes. Anything else?
Finally, we have aromatics, which are typically cyclic conjugated systems, with benzene being the most iconic example.
Benzene rings. Very common.
Incredibly common. These compounds possess a special enhanced stability due to extensive electron delocalization in their pi systems, resonance on steroids, essentially. While a deeper understanding of aromaticity comes in later chapters, it's good to be aware of them from the start as a distinct and incredibly important class with unique reactivity.
It's clear that the type of carbon-carbon bonding profoundly changes the reactivity and overall physical and chemical properties of the molecule. This basic classification really sets the stage.
It does. It's the first structural feature to look for, setting the stage for understanding all the more complex structures we'll encounter and even their practical applications.
Okay, last major concept for today, isomerism. One of the most intriguing and frankly mind-bending concepts in organic chemistry
It can definitely twist your brain a bit at first.
is that two entirely different compounds can possess the exact same molecular formula, yet have completely distinct structures and, consequently, completely different properties. That's the essence of isomerism.
Where the magic and complexity truly begin to unfold.
It demonstrates how subtle differences in arrangement can lead to profound differences in nature.
Yes, isomers are defined simply as different compounds with the same molecular formula, same parts list, different assembly instructions.
Right. And your sources highlight two major overarching classes of isomers.
Yes, and distinguishing between them is absolutely crucial because the implications of each are vast. The first class is constitutional isomers, sometimes also called structural isomers.
Constitutional. Okay.
These compounds share the same molecular formula, but they differ in the connectivity of their atoms, meaning the atoms are bonded together in a different order.
Different connections. Can you give an example?
Sure. Consider the molecular formula C4H10. We could have N-butane, a straight chain of 4 carbons. Or we could have isobutane, also called 2-methylpropane, where 3 carbons are in a chain and one is branched off the central carbon.
Both C4H10, but one is straight, one is branched.
Exactly. Same count of each type of atom, but their atoms are connected differently, leading to different boiling points, melting points, and even different chemical properties. They are truly different compounds.
Okay, so constitutional isomers differ in how atoms are connected. What's the second class?
The second major class delves even deeper into the three-dimensional arrangement. These are stereoisomers, also known as configurational isomers.
Stereoisomers.
And these compounds have the same connectivity, the atoms are bonded together in the exact same order, but they differ solely in the spatial arrangement of their atoms. How the atoms are oriented in three-dimensional space makes them distinct molecules.
Same connections, different 3D shape.
Precisely. And this subtle difference can lead to dramatically different physical, chemical, and crucially biological properties.
And a common type of stereoisomerism is cis-trans isomerism, which we touched on when discussing double bonds and their rigidity. That falls under stereoisomers.
Exactly. Cis-trans isomers, often called geometric isomers, are a very important and common type of stereoisomerism, particularly for alkenes.
Because of that rigid double bond.
Yes. Due to the inherent rigidity of a carbon-carbon double bond, that inability to freely rotate, we discussed earlier with pi bonds, groups attached to those double bonded carbons can be fixed in specific positions relative to that bond.
Okay, how do cis and trans differ?
If similar groups attached to the double bond carbons are on the same side of the double bond, imagine drawing a line through the double bond, it's defined as the cis isomer.
Yeah.
If they are on opposite sides, it's the trans isomer.
Same side, cis, opposite sides of trans. Can you give us a concrete example?
Think of cis but 2-an and trans but 2-an. Both have the molecular formula C4H8 and the same connectivity. CH3, CH3. The double bond is between the second and third carbons. But in cis but 2-in, the two methyl groups, CH3, are on the same side of the double bond. In trans but 2-in, they're on opposite sides.
Same formula, same connections, just different arrangement around the double bond.
Exactly. And these are distinct compounds with different physical properties. Cis but 2-in has a slightly higher boiling point than trans but 2-in, for example, due to differences in molecular shape and polarity. More importantly, they can exhibit different chemical reactivities and cannot be interconverted without breaking bonds, which requires significant energy.
That's fascinating. So the study of stereoisomers or stereochemistry isn't just an academic exercise, it's hugely relevant, isn't it? It feels like it underpins so much in biology and medicine.
It is absolutely paramount. Stereochemistry influences everything from biological activity, for instance, how enzymes in your body recognize and interact with only one specific enantiomer, which is another critical type of stereoisomer, non-superimposable mirror images.
Ah, the handedness of molecules.
Exactly. Enzymes often only fit one hand. Consider a famous historical example, the drug thalidomide. One enantiomer was a highly effective sedative.
Right, the intended use.
While the other enantiomer, its mirror image, a stereoisomer with the exact same connectivity but a different 3D shape, tragically caused severe birth defects.
A devastating example of stereochemistry's importance.
It highlighted in the most profound way possible that a molecule's precise three-dimensional shape is often the key to its function, or indeed its danger. Stereoisomerism also plays a vital role in the properties of synthetic polymers, and advanced materials controlling the 3D structure gives you control over the material's properties.
So isomerism truly adds another profound layer of complexity and fascination to the molecular world. It really demonstrates how even tiny, subtle differences in the three-dimensional arrangement of atoms, while maintaining the same molecular formula, can lead to vastly different chemical and physical properties in nature.
With sometimes life-altering consequences. It's a testament to the intricate dance of molecules and the importance of shape.
Wow, what a journey. We've truly journeyed from the invisible world of electrons and orbitals through the elegant rules that govern covalent bonding and electron distribution.
Hybridization, resonance, electron pushing.
Explored the dynamic language of acids and bases, pKi values.
And finally, delved into the diverse structural frameworks that carbon can form, including the mind-bending concept of isomerism. You now possess a powerful conceptual toolkit. With these foundational insights, you can begin to look at a molecular formula or a structure and start to predict its three-dimensional shape, its potential for electron delocalization, how it might behave as an acid or base.
And what functional groups define its characteristic reactivity.
Exactly. This foundational understanding is not just theoretical. It is invaluable for making sense of the entire field of organic chemistry and connecting it to the world around you.
This deep dive has truly laid the groundwork for everything else you'll encounter in organic chemistry. It's designed to be a shortcut, helping you see the underlying elegance and patterns in what might initially appear to be overwhelming complexity.
But is in fact incredibly logical and, dare I say, beautiful.
I agree. It really is.
And here's a thought to take with you, something to ponder further. Given that these fundamental principles, the versatility of carbon, the rules of hybridization, the dynamic nature of electron pushing, resonance, acidity, functional groups, and the subtle differences in geometry leading to isomers.
All the things we talked about.
Right. Given that all this allows for such an endless variety of carbon compounds, how might even tiny subtle differences, a slightly different pKi, a minor resonance contributor having a bit more weight, a cis bond instead of a trans bond,
Small tweaks.
how might those small tweaks lead to profound and often unexpected differences in the behavior of drugs, the properties of materials we use every day, or even the intricate life-sustaining functions of biological systems within living organisms?
That's a truly deep thought worth exploring further on your own. Knowing that you now have the fundamental insights and the language to begin to unravel those complex molecular mysteries. Thank you for joining us on this deep dive.
We hope you feel much more informed and, perhaps, a little more fascinated by the molecular world.